Okay, so here's the next one. And you may see like this one is maybe it's a combination between the two of them, because you see we have one R reference at the top, but we also have one R reference at the bottom. Okay, but we also have a V in and R1. Remember, don't focus on formulas. When you see an amplifier, just try to keep an open mind and seeing as something perfectly new. So, what we do here? Well, we just apply the same steps. Cut the current at the pins, mark the nodes. Positive, that means it's V1, negative means it's V2. So yeah, remember, be very careful on the polarities as well, because sometimes it actually really throws me off when some exercises they have it at the top, the positive at the top and the negative at the bottom, but some of them just flip it over and it's having the positive at the bottom and the negative at the top. I mean, usually you do this to like save space when drawing the circuit, so you don't like spread a lot, but just be careful on the signs. And remember, as long as you remember that V1 is at the positive pin, you should be fine. Now, so what we do here, well, V1 is in here on this side, but there are 0 volts going through it, so V1 will be 0 volts here. So then 0 volts will be equal with V1, and that will be equal with V2. And then we need to apply Kirchhoff's current law. Kirchhoff's current law again on this one here, and this not here because there's no current going through here. And then this I, okay, then on this side, this current I, they are, you know, they are different. So this I, that will be V in minus, let's just put 0 volts because we know that V out is equal to 0 volts divided by the resistance R1. Then that will be equal with this current on the other side, which is equal with let's see here, 0 volts, V in, V2 point, so 0 volts minus V out, and the resistance in between, which is RF. Alright, so then therefore V out over V in, it's equal with minus RF over R1. And you may say, well, Alex, what's the point of this resistor here then? If you already solved the problem with only one equation straight away that we already did it, this doesn't really look like an inverting amplifier because it's got this resistor here. Well, I drew this one here to throw you off, because another way to draw this circuit, it's also to draw something similar to this. And sorry for my drawing skills, I am not that good at drawing diagrams on the fly. Not even drawing them like off camera, I'm not that good, but still, at least they are more eligible. So then this will be a ground, because RF is connected to the ground, and then RF is connected here. Then it's a ground connected to the positive side because it's 0 volts, and then is the normal circuit connected on this side here with RF in this side meeting here, RF, and R1 on this side here with the plus minus V in that is connected to ground as well. Okay, sorry, you didn't see all of that. There you go. So then what does this remind you of? Well, if we go to our previous one, you can see that this RF, it's actually this RL in here. We can just say that instead of RF, this is RL. Doesn't really make a difference because it's connected at the V out point, which is this here, and from the V out point it's connected straight to ground. So it's basically RL, but instead of going downwards, it's upside down, so it's in the upside. Okay, again, this one was a very simple and very short one. It took us only 5 minutes to do it, and we can see that even though it doesn't look like it, it's actually an inverting amplifier. But again, we don't really care about the terms. What we care about is applying the formula and getting the answer that we want. Alright, I'll pause here and we'll go to the next one. Okay, next one. Well, on this one you can already see it's more interesting, because not only that the way that they are laid out is very different, but also there are two voltage sources instead of one voltage source. And again, if you are like kind of the person that wants to go with the formulas, you'll have a hard time finding the values of these two voltages, or like of the amplification with the voltages. I mean, it's technically called a comparator, I think, but again, I would prefer if you like create your own formulas. And you may say, well, how do we calculate this? I mean, there are two voltages. And again, here I come saying, well, you should watch the first 30 videos that I uploaded on the channel, because not only that, on the previous exercises we applied Kirchhoff's current law, and we also applied nodal analysis, which the two of them are very similar. I'm not really sure actually what's the difference, but still, we applied the two of them. Now we are going to apply superposition to it. And you may say, can you apply superposition to a circuit with an op-amplifier? And what I'm going to say is, yes, of course you can. You can apply superposition to many types of circuits that has two voltage sources. That's why it's also very popular and very widely used. Now, if you apply superposition, you know that the rules of superposition is to calculate only using one of the sources while eliminating all the other sources. So we are going to use V1 and we have to eliminate V2 and replace it with something else, and we are going to replace it with ground. Then let's see here. So again, I will quickly try to redraw it nicely. So it's a minus here, it's a plus here. There will be V out 1 because we'll use this one will be the voltage V1. There will be a ground where V2 was, and it will be connected to a resistor that's connected here, and then on the top goes another resistor, which that one will be connected here, and here will be the RL, even though we don't really use it. Actually, we won't use it for this one because we don't want to find the current. V inst is the same, a resistance here, then it splits down here. This is the ground here, and it connects here. Alright, so actually let me put like this one is R1, this one is R2, this one is R3, this one is R4. Okay, so what do we do now? Well, we just apply the op-amplifier rules. No current going through here. That means the current goes through V1 to V4 straight down the ground like this. But also we mark the nodes, so the nodes are in here, and the positive pin, so this will be V1, and this negative pin, so that will be V2. Actually that will make it really confusing, sorry about that. If I start putting V1 and V2, you'll mistake it with these two, V1 and V2. Let's call it VP and VN. There you go. That will be simpler. Right. Oh yeah, the reason I put this one, the infinite sign to it, is because it's like an ideal op amplifier, like it's got infinite resistance inside of it. Don't worry about that. You won't have any problems like resistance or the way that op amplifiers are built, because we are doing it in a theoretical way. Like this is on paper, so on paper it's perfectly balanced. When you build an actual circuit of it, then it won't be perfectly balanced. It will have like problems like leakages, and it won't always give you the exact value that you calculated for it because of the fabrication of the op amplifier. The thing is, like, this one is the ideal one. This one will be the perfect amplifier that doesn't exist in the real world, but you use it to calculate it on paper. So then let's get started. So what we need to know, VP will be, let's do like that. VP, it's equal with Vn, so VP it's V1, and that will be equal with the value of V1. It doesn't really help us a lot right now, but it will help us in the future. So what do we do here? Well, first we need to find the value of VP, and actually it's not V1, because VP, the current I that has this direction, will first go through R3. That means the voltage here at point VP will be less than the voltage coming from V1. Yes, that's the problem, yes. So then I need to apply voltage, the voltage divider rule. So then VP voltage here will be equal with R4 times V1 over R3 plus R4. Yes, and by doing so, by doing the voltage divider rule, we will get this voltage at this node here at VP, and then VP, because it's equal with Vn, then this value here will be also for this point here. It might look complicated right now, but it's actually really simple because we just simply write VP, and at the very end of the equation we are going to come back to this one here, and you'll see in a second what I mean by that. So then, and let's see here, we need to calculate it from this side here, because this side is actually connected to V out. This is the side that the current goes through. So then this will be the first I, and this one will be the second I that goes out of the node. So 0 minus Vn divided by R1, because it's between them, it's equal with Vn minus VO1, Vout1, divided by R2, because R2 is between them. Therefore, minus Vn divided by R1 will be equal with Vn over R2 minus Vout1 over R2. Okay, so then what we can do next is we can multiply by R2 and then get rid of the R2s in here. So then therefore minus Vn times, actually let's just put in bracket, times R2, there you go, times R2 over R1 will be equal with Vn minus Vout, and then we divide by Vn to get rid of the Vn here, and to also get rid of the Vn in here. So now you can say therefore minus R2 over R1 would be equal with 1 minus VO over Vn. Therefore VO over Vn will be equal with 1 plus R2 over R1. Therefore VO1 will be equal with 1 plus R2 over R1 multiplied by Vn. And as you know, Vn is equal to Vp, so it will be this value here. But we won't really put this here because to make the problem more complicated, and it won't serve any purpose. Because this is purely theoretical, this is just creating the formula for it. Because if we actually had numbers on it, then we can just plug in the numbers and do the calculation for Vn right here. Anyway, let's see, let me turn the page, because now we need to go to the second one. So this one was for VO1, now we need to do it for VO2. So I'll go on this side here. So now we have an amplifier here, I'll draw one, minus plus infinity here, long line for the output V out. Let's see here. So now V2 stays the same. There will be R1 here. It's connected right here. Goes up through a second resistance. Then it goes down here. And now V1 will be replaced with the ground. Then R3 here. Connected to the plus side. And another resistor to the ground here. R4. So R1, R2, R3, and lastly R4. Alright, so again, let's apply the rules. There's no current going through the pins. These are the two nodes. This one still stays as VP, and this has Vn. Okay, and let's put prime to them, so prime. So again, we don't make the same mistake. And because this is 0 volts and this is 0 volts, then simply at this point there will be just 0 volts. So 0 volts will be equal with Vp prime, which is equal with Vn prime. So there are 0 volts in here as well. So then V2 minus Vn prime divided by R1 will be equal with Vn prime minus VO2 divided by R2. Again, simplifying Kirchhoff's, I here, this one goes in this direction, this one comes in. And simply to find the value V out, we do V2 minus V in divided by the resistance R1 and Vn minus VO2, this VO2, divided by the resistance R2. Okay, therefore V2 minus 0 divided by R1 is equal to 0 minus VO2 divided by R2. Okay, then R2 over R1 will be equal to minus VO2 divided by R2. Therefore, minus VO2 will be equal with R2 times V2 divided by R1. And then therefore, VO2 will be equal with minus R2 times V2 divided by R1. Alright, just again moving some variables around, simply multiplying this one by R2, so we get these values here. Then next we can say that V out will be equal with VO1 plus VO2, just like superposition. At the end of it you get your two values that you want to know. So we know VO2 and we also know VO1 from the first half. And now what we have to do is to simply add them together. So then V out will be equal with 1 plus R2 over R1 multiplied by, very important, this is the first part, but now we need to put in the this value here as well, Vn value, which is also seen as Vp with the voltage divider rule for Vn. So then that will be multiplied by R4 times V1 divided by R3 plus R4. And then we add it with the value of V2, and the value of V2 is simply minus R2 times V2 divided by R1. Alright, now what we need to do is to simplify them. So what we can do to simplify is to get out the V's. V out will be equal with 1 plus R2 over R1 multiplied by R4 times V1 over R3 plus R4 multiplied by V1 minus R2 over R1 multiplied by V2. And here will be a surprise for you that you didn't expect. There is actually a fifth rule in here. So these are the first four ones, and now the fifth rule, it's A1 times V1 is equal with plus A2 multiplied by V2. And you may say like, well, what does this rule means? Well, this rule will give you the voltage output. This rule is specifically for comparators. And what do I mean by that? Well, A1 that will be the gain inside the first voltage, inside the first superposition. A2 will be the gain inside the second superposition, and both of them are depending on their respective voltage inputs. So A1 is multiplied by V1, so it's depending to V1, and then A2 is depending to V2. If it wasn't a comparative OP-Amplifier or comparator, then V1 will be 0, which means the gain A1 will be 0. So this applies only with comparator amplifiers, you know, the ones that have two voltages going in, V1 and V2. If there is only one of them, if this one was connected to ground, then you don't apply this, you just apply the first four ones. This fifth one is very You use it only when you actually need it, when there's two voltages above the ends. So now, what does this formula mean? Like, can we apply it? And the answer is, of course, yes. Why? Because this first section here, it's to simply calculate the gain inside A1, and then we'll multiply by V1 here, minus, and then this small section here, actually it's a plus, but then let's put it like that, plus, and because it's a negative, there'll be an A2, and we multiply it by V2. Again, very, very interesting, isn't it? So these are the gains and the voltages here. So we can also rewrite it as A1 is equal with 1 plus R2 over R1 multiplied by R4 over R3 plus R4. And then A2 will be equal with minus R2 over R1, and that's it. And you may say like, well, Alex, what's the point of this? Well, let's say that you'll see in future problems as well. Let's say you want a specific gain. You want V1 to have a gain of 2, but you want V2 to have a gain of 4. Well, again, you can manipulate these resistors here, 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 and here, these 4 resistors, to give you the whatever gain you wish to gain. And we don't really need to simplify this further because we can't really simplify it further. This is the simplest I can come up with. But again, we are going to get formula similar to this one because we want, sometimes you want a specific type of gain. Now, something cool is that we can make this circuit to have the formula of V out equal with V1 minus V2, and I mean like the proper sources. Like we can create this circuit to be simply be equal with V out will be equal with V1 minus V2. And you may say like, well, Alex, how do you do something like this? Very simple. We change all of the resistors to the same value. And those are like kind of like cool tricks you can do with OP-Amplifiers if like switch all the values to their same value. No, all the resistors to their same value. For example, like for A1, what if I change it to the same values? So let me like separate it here with a line or whatever. There you go. So let's say that A1 will be equal with 1 plus R over R multiplied by R over R plus R. And we'll multiply this one by V1. Then what we get is simply R over R, there'll be another one, so there'll be a 2 here. And then R plus R, there'll be R over 2R, so that will simply be equal with 1 over R multiplied by 1 over R multiplied by V1. So that'll be 2R, that'll be 6R. Yeah, I think that's correct, yeah. Okay. And then that will be equal with 2 over R, that's V1. Now if we do it for A2, then you get a minus R over R multiplied by V2. Then that will be equal with a minus 1 times V2. And then, yeah, I don't know where I was going with this. Because let's see, so then this R will be multiplied, so this R will be 2 because it will be 1 plus 1 multiplied by R over R plus R, so that will be 1R, wouldn't it? And this one will be 2R, but this one it's minus 1R. And maybe if you switch this on to R values, then I guess you can say it's like 2 over R minus R over R, but it doesn't really make sense. Maybe like 2 R over R. Okay, just forget about this part. I saw it when I'm doing like, so I did the same mistake as I did before. I saw the formula when I was doing, actually I just cut this one out. Okay, so yeah, this was it. No, it's not fair. Okay, I'll be honest. I looked at competitors, the formula for it, and I saw that the formula V out is equal to V1 minus V2. It will appear if all the resistors were equal, if all of them had the same value. But I don't know why it doesn't really work. Like if I replace these values here with R, I should eventually get the same value, but it doesn't really work. Maybe I just calculated wrong. I mean, you can tell me in the comments if you want. But yeah, it's not really something important, because you can come to this conclusion if you see this circuit that has all the R values like the same. But anyway, so this one was calculating a competitor OP-Amplifier with two different voltages. Alright, I'll pause here again. Okay, here it's a different one, and this one, it's a simple summing amplifier. And why it's so simple? Well, it's got only two voltages to sum up. And you may say, what was the difference between the summing amplifier and the competitor amplifier that we just did? The difference is quite clear. In the summing amplifier, yes, you have multiple voltages, but these voltages are only going through one pin, while in a competitor amplifier, both pins have their own voltage sources. But because one of the pins is connected to ground, then there's only one voltage coming inside this pin here. So let's get started. But again, first step, apply the rules. No current going through here. Those are the two nodes. This node will be V1 because of the positive. This one will be V2. Okay. And now, actually, I see that now we have something different. So we'll have one current I1 coming through here, another current I2 coming through here, and that will give us the current I. And remember that the same current I will come also out of the node here. So now we have an extra step because we have to discover the value of I in here. So let's get started. V1 is going to ground, so it will be 0 volts. So then 0 will be equal with V1, which is equal to V2. And I will be equal with I1 plus I2. Let's do it properly actually. So this is the node. I1 is coming in, so it's positive. I2 is coming in, so it's positive plus I2. But I it's coming out, so it's negative minus I, and those are equal to 0. So you can really just ask I1 plus I2 equal with I. Okay, in case you didn't realize that this is how we do it. Again, if you struggle understanding why we do this, like why we apply this type of formula, you need to revise Kirchhoff's current law and node analysis, to be honest. Because, I don't know, you can't really go further away without the basics. So let's keep going. We apply Kirchhoff's current law now, Kirchhoff's current law. And we need to find this I in here, because this I is equal with that I there. So we can say I is equal with I, but we replace the first I in here with this formula here. Therefore, Kirchhoff's current law, two dots here, will be I1 plus I2, and that will be equal with I. Okay. Now, we simply apply what we applied before, which was to determine the currents by using the resistance and voltages. So this dot here, it's again equal with V2, so both of them I have the same voltage. So we can simply write it as V prime 1, so V prime 1 minus V2 divided by R1 plus V2 prime, so V prime 2 minus V2 divided by R2. So that's for I1 and I2, and they will be equal with the value of I, and the value of I will be V2 minus VO divided by RF. Okay, so we will need to like simplify it, so we can divide it by V2. So divide by V2, even though it's 0. So we can just do, actually yeah, it's 0. I could have just like did the 0 way, but it's fine. It's basically the same thing. So V prime 1 over R1 plus V prime 2 over R2 will be equal with VO minus VO over RF. Alright, next step will be to multiply by RF. So multiply by RF, then will be minus VO equal with RF multiplied by bracket V prime 1 over R1 plus V prime 2 over R2. Then therefore we just switch signs and we implement RF in both of them. Therefore VO will be equal with V1 prime times RF over R1 plus V prime 2 times RF over R2. And remember that they are still at the minus sign because we inverted, we made the VO positive. And that will be the formula for the summing amplifier. Again, very simple. I don't think I can simplify it further away from this. I think this is the simplest you can get. But it's that's it. Quite simple, isn't it? Took us only 5 minutes. A lot shorter than the superposition one. But remember, this is summing amplifier. So I can add an n number of values here. I can add as many values as I wish. Anyway, thanks for watching, and I'll see you on the next exercise. Because surprisingly enough, I'm only halfway done through them. I got like 13 exercises ready for it. And then this one it's exercise 6. So yeah, see you in a bit. Okay, this is exercise 7. Again, another summing amplifier. But this one is actually a little bit more different. And why is that? Well, we have 3 voltages now, but the big difference is not that one, but we will add on to it to make it do whatever we want it to do. Okay, so then let's get started. I'll get the red pen. We cut here, so there's no current going through here. This is the positive, so this will be V1. This is the negative, so this will be V2. And these are the nodes, and it's connected to ground, so both of them will be 0 volts. So at this point here it will be 0 volts as well because it's connected to V2. Okay, there will be 3 currents. There will be current I1, there will be current I2, and there will be current I3 going through it. And out of it will come current I. And current I will go to the top here as well. And then we can determine the values. And again, it's very simple because we apply the same principles. So I1 is coming in, so it's positive, plus I2 is coming again in, it's positive. I3 is coming in, so it's positive, so it'll be I3. I it's coming out, so that is the only negative, and those will be equal to 0. So we can arrange it as I1 plus I2 plus I3 is equal with I. And again, we apply the same Kirchhoff's current law rule, and all we need to do is just calculate. So I1 will be V1 minus 0 divided by R1. So V1 minus 0 divided by R1 plus I2 will be V2 minus 0 divided by R2. V2 minus 0 divided by R2. And V3 will be, and I3 will be V3 minus 0 divided by R3. V3 minus 0 divided by R3. And we add them together, this plus again, and that will be equal with I. Therefore, V1 over R1 plus V2 over R2 plus V3 over R3 will simply be equal with V out, 0 volts minus V out divided by RF. So 0 volts minus V out divided by RF. Okay, therefore VO will be equal with minus RF times V1 over R1 plus V2 over R2 plus V3 over R3, and that will be equal to minus RF times V1 over R1 plus RF times V2 over R2 plus RF times V3 over R3. Alright, so there we have it, that's the answer. And remember, if it's a negative value, that means it amplifies in the reverse direction. For example, if this was a plus and this was 12, if this value gave us 12, then it will amplify by 12. But because it's a minus, it's amplified by minus 12, so that will make it an inverse. That's why it's also called the inverse amplifiers and so on. Alright, now what I wanted to show you, because this was very simple, it was very basic and similar to the previous one, is that we can actually properly transform them. So then, if I let's say, let me put here like a space between them. Let's say if I want the format to be V out equal with minus V1 plus V2 plus V3. Then I need to make all the resistors equal to get this value. Okay, and to remove the minus, so remove minus, I will add a buffer. Okay, so let me actually draw a circuit that follows this formula here. And look, I know on my, yeah, I think that's it, isn't it? Yeah, I was looking at my notes again, and let me see. Oh yeah, so you know my previous example that okay, let me think what I want to say. So in my previous exercise, I felt bad that I didn't know how to explain how it works, how this V1, how to create this formula here. But it's mathematically simpler here, because we have this formula format here. Okay, so let me show you actually, if I still have the page. Just a second. Yeah, there it is. Because like for this exercise, I try to say that it applies here as well, but actually it doesn't, because in the end I couldn't figure it out, you know. But in this one here, I can actually prove it does equal this value here. And how do I do this? Well, so I keep moving here. Well, I simply make all of these values R values. So if I take this formula here, if I take VO, it's equal with minus RF times V1 over R1 plus RF times V2 over R2 plus RF times V3 over R3. Okay, and I replace them with the same value, so I'll make all of them R. I'll get something like this: R times V1 over R plus R times V2 over R plus R times V3 over R. And because the R's cancel each other, they'll be equal to 1, and then V1 will be multiplied by 1, so all V's will stay the same because they'll be multiplied by the value of 1. So then we'll get VO will be equal with minus V1 plus V2 plus V3, and that'll give us this formula right here. I don't know why, I'm not sure, like last time I tried to do it for this example here, I calculated it wrong. Or probably it actually didn't work. It didn't work because I had this resistor R4 in here and this resistor R3 in here, and it didn't allow me to do it that way. And that's why it's allowing me to do it here, because there's no resistance at the bottom side. It's only 0 volts to it, it's only a ground. And probably that's the reason why I can do it here for this type, but not for this type here. I guess it's just to show you that rules don't, I mean specific rules, like it don't always apply. For example, even though it is a comparator and if I would replace all of them with just the R values, it probably wouldn't work as well as it does work here with the summing amplifier. And probably that rule that I read, that if you replace all the resistors with the same R value, probably only works with this type of only with summing amplifiers, and it doesn't work with all amplifiers. It doesn't work with comparator amplifiers. Anyway, sorry for me rambling. I don't know, I guess I wanted to clarify, and I wanted to say that yes, I did a mistake on the previous exercise, that I didn't know the proper answer for it, and I should have like checked before I recorded myself. Anyway, so let's keep going. Now we need to add a buffer to the end of it, so let's redo the circuit with a buffer this time. It is going to be quite big. So there will be one amplifier here. There will be V1 here with the resistance, like this. So there will be minus, there will be plus, infinity here. This one, it's other dot, other source, and another source here. All of them connected here, connected to this one. So this V1, V2, V3. Okay, and all of them will be R, the same R value. And this will be just connected to ground, 0V. Then this one will be again an R connected to the top, R, and we'll have to connect it to another resistor R here, because that's how buffers work. I mean, you can just leave it as a bare wire if you want, but I wouldn't suggest that, because still maybe you don't want that much current going through it. Maybe you want to limit the current, or maybe you just want to protect the component. So it's better to just put like a resistance. The only important thing is that the resistance is the exact same value. So again, it's like 1 by 1, you know, 1 to 1. So this one will be the voltage output, and this one will be the, I actually need to put on here, and this will be the RLs, RL, and another RL in here. Alright, and then add this dot here where the first V out was. Then this one would have been VO equal with minus V1 plus V2 plus V3. Alright, but now we are at this VO here. It goes through another invert, and invert will just make it the opposite sign. So then that will be VO equal with V1 plus V2 plus V3. And there we have it. We got rid of the minus sign from this formula here, and you simplify to a formula like this one here. To be honest, like if you want to have a formula like this one here, I don't really see the point of like using an amplifier to get that, because you can again literally just add the voltages together, just connect the 3 voltages together in series and get that voltage output. But who knows, maybe some people want to have something like that. Maybe they want to create a switch where it goes to this value. I mean, I'm not sure. It depends, or maybe it's more of a benefit of doing that, doing it this way. I'm not sure, but still, it's everybody what they want to do. Now, another cool thing you can do with summing amplifiers, and I'll go on the other page, is that maybe I want to have an output, let me write it right, a VO that's equal with the average of all V inputs. So my voltage output will be the average of all the voltages that go in. And again, let's write the base formula. So V out will be equal with minus RF over R1 times V1 plus RF over R2 times V2 plus RF over R3 times V3. Okay, and here is the thing. Now, instead of replacing all the components with R values, now we are going to replace them with the RF values. And the rule to apply here will be like, we'll have to change R1 to be equal with R2 to be equal with R3 to be equal with the n number of RF. And because we have only 3 voltage inputs, V1, V2 and V3, the n number of RF will simply be equal with 3 RF. Alright? And again, if we just put like, if we rewrite it with these values here, then VO would be equal with RF divided by 3 RF times V1 plus RF divided by 3 RF times V2 plus RF divided by 3 RF times V3. Okay, and then what we do with, we eliminate these values here, the RF will get cancelled and we'll be left with V out will be equal with minus V1 plus V2 plus V3 divided by 3, the only number that's left, because 1 over 2 will be left, and then we'll obviously get the average by doing so, because that's the formula of the average. And how will that look in an actual circuit? Well, remember that RF at the top stays unchanged. The only values that we change is R1, R2, R3 and etc. for the end of the RF. So remember that RF has to be both in the same value. So let's go to this one so I don't need to draw again. It will put like 3 RF at the beginning of all of them, and then this will become RF values and they'll stay the same. And that's the only difference. The inputs will be connected with resistances that are 3 or 4 or 5 times bigger than the RF, depending on how many sources are there. And that way we'll get a formula that will give us the voltage output, the average value of gain. Okay, again, it's a bit strange, but I think there are a few uses for it. I didn't really use amplifiers that much as well during university, and I guess that's why I'm not very well prepared for them, because usually when I did a circuit and I needed an amplifier, it was very simple, you know. I simply just put like the amplifier in the center, a resistor connected to two of them, another resistor connected to the source, and just calculate the resistances for the gain that I want to get, and that's it. While these ones are more difficult because, you know, you have multiple voltage sources or you have two voltage sources in both of them. But I mean, like, I didn't really work with amplifiers that much. I did a bit of theory of it, but that's it really. We moved quite quickly to amplifiers. We learned the basics of them, and then we just moved straight away to transistors. But again, I think we need to better understand amplifiers to be able to understand transistors. That's why I'm going to spend quite a while on this. So hopefully you understand how to calculate the sum amplifier for 3 of them or 4 of them, or how many voltage inputs are in here. And I hope you understand how to change this this circuit, the formula of it, into a simple V out is equal to minus V1 plus V2 plus V3. And also I hope you understand how to change the sign, how to make it from a minus to plus, or how to make it from a plus to a minus by simply adding invert buffers to it. Okay, again, I'll pause here and we are going to go to the next exercise.